Okay, so I am not currently here, but I wanted to provide you with some of the notes we would do if I were on average atomic mass. So these are those decimal numbers that show up on the periodic table, where they come from, how we can calculate them. So we can take a look at the first example. Over here, this is the number that we are looking for. So we have this problem. Chlorine exists as two isotopes. There's chlorine 35, which has a mass of 34.969 atomic mass units and a relative abundance of 75.77%. Chlorine 37 has a mass of 36.966 atomic mass units and a relative abundance of 24.23%. So what this tells us is we have two possible versions of chlorine. They have different masses. And when we look at their relative abundances, all this really tells us is, hey, 75.77% of all the chlorine in the universe weighs about 35 units, whereas 24.23% of it weighs about 37 units. So the thing that you would think to do for an average is, well, we have our two masses. We have 34.969 plus, where did it go? 36.966. We got two data points. You would think to take this, add them up, divide by 2. Unfortunately, we can't do this. When you solve the problem like that, you're assuming equal percentages. And so when you look at our two numbers here, 75.77, 24.23, those are not equal to each other. So we can't do that. We have to use these percentages based on their actual numbers. So in order to do that, we're going to turn both of those percentages into decimals. So for our first one, 75.77, that's going to become 0.7577 as a decimal. 24.23 becomes 0.2423 as a decimal. And we're going to apply these to the masses that we have. So for that first one, we're going to say 75% or 75.7577 of all the chlorine in the universe exists as this mass, 34.969. So this means 75.77% comes from this mass. There we go. It's not the only thing, though. We also have the other isotope at 24.23%. And that one has a mass of 36.966. And so this is good. We've accounted for all 100% of the stuff. We've got both isotopes. And now it's a matter of multiplying. So multiply first two values, your percent and your mass. Your second two values, your percent and your mass. We're going to add those together. And when you do this, we should get 35.45 AMU, which is pretty good because, well, when you check against the periodic table, well, that's pretty much the same number, so you can guarantee that you are right. So this is generally how we want to approach these problems. Focus on the percentages and their corresponding masses, multiply, and then make sure you're adding up all those parts so we include all of the isotopes that are going to be averaged. So take a moment, pause the video, look at the table here. This is for silicon instead of chlorine, and try to use the same process in order to solve this. And then you can check in a little bit. I'll be doing the same thing. All right, so you can see the majority of the silicon is 92.23%, has a mass of about 28 atomic mass units. So again, take our percentages, convert them into decimals, 0.9223 times its exact weight, 27.976927. Now you know why I don't like us using so many decimals, because that's kind of annoying. But there's our first one. For our second isotope, the one that weighs about 29, be careful when you are dealing with small percentages. 4.67, you still have to move it 2 decimal places, so that 0 is going to fill in that space. So 0.0467 times its corresponding mass, so 28.976495. All right, and we got one more to do. Plus, same deal for our percentages. It's going to be 0.0310 times 29.973770. Yikes. But we have accounted for all 3 isotopes. We have all 100% of the stuff dealt with. And when you run this through, we should get about 28.085 AMU, atomic mass units. And if you check against the periodic table, that should be correct. So that looks all right. So last one, this is a little bit different in that it does not explicitly tell you what the percentages are. We have some element X, and there's 100 atoms of element X in this sample with a mass equal to 12. And then there are 10 atoms with a mass equal to 14. And so we want to find the percentage of each of these. Now, probably a good idea to find the total. We want to know how many total are in our sample, and overall at whatever element X, we've got 110 total atoms present. So let's focus just on the first one here. If we want to know, percentage or really decimal-wise, what we have, 110, 100 out of 110, we're going to have 90.9% of our total, which means, well, they got to add it to 100. 10 out of 110 is going to be 9.1%. So now we have our percentages. Remember, the first one corresponded to a mass of 12. The second one corresponded to a mass of 14. And we can solve this problem just like any other problem so far. We've got 0.909 times 12. And we have, remember, you got to move it over 2 places, so 0.091 times 14. And if you had to predict which one of these was going to contribute more, what it should be closer to, I would say this is probably closer to 12 because the majority of the element X has a mass of 12. So let's see, when we add those up, I end up with 12.182 AMU, and that fits my prediction. That is closer to 12 than it is to 14 because, well, we've got a much higher abundance here. Which means we're going to be closer to that value. So, hope things are going all right. Use this time to solve those practice problems in the back and get those checked before you leave today. Make sure we're on the right page here. So, sounds good. Thank you. Hope the rest of the week goes well.